Boundary layers. We said that the boundary layer shape in laminar and turbulent flows are different, and you can see it in here. We can draw these two profile shapes for laminar and turbulent flows. In turbulent boundary layer, you have a fuller profile. You can see it is um, fuller. Fuller means the velocities are much higher. It's not parabolic like in laminar flow. And finding the boundary layer velocity profile shape near the wall is challenging. There are different models actually to find this profile. Regarding the drag application in pipe flow, of course, if it is in pipe flow, drag for internal flows, uh, and we are more interested in kinetic energy losses, and we are more interested in terms of resistance generated inside the pipe, and resistance are due to the wall boundary layer. So they are related to the shear stresses. As you can see in here, you have the shear stresses generated near the walls. We know that very fundamentally your tau wall, you may remember it from fluid classes, is related to the velocity gradient, not the velocity gradient near the wall. This is the y-axis. Okay, this is the y-axis, and you have the mean velocity gradient. So this bar sign over the velocity shows it is a mean velocity gradient. And when you multiply it by the viscosity, it will give you the shear stress near the wall. So what's the physical reason that you do not have a velocity profile of turbulent flow? This profile of turbulent flow is similar to the profile of laminar flow. What's the physical reason? Can anyone answer to me? Can anyone say that, okay, because of this physical reason, these profiles are different? You can't explain. You can or you can't. Is there a typo or you cannot? You can't explain. Okay, so I will explain. It's related with mixing. And I said that when you have mixing, you are not only mixing scalars like dye, like paint or temperature, you also mix vectorial quantities like momentum. You remember I just said this. If you see the profile, the laminar profile, you can directly see that there is no mixing because you have very high velocities and very high velocities in here and very low velocities in here. Okay, it directly tells you that there is no mixing because the velocities are very different at the edge of the boundary layer and in here. Okay, so there is no mixing because you have these high velocities and low velocities and they are not really interacting with each other. If they would be interacting, then the the layer, the faster layer or the higher momentum layer would transfer some of its momentum to the lower part, and the lower layer would drag or hold back the upper layer. So in turbulence, there is a lot of interaction between fluid layers, which could be moving with different momentum values. So when there is a lot of mixing, everything gets equalized or gets close to each other. When momentum distribution gets more uniform because of this equalization, you will end up with a flat profile in the mean values. But the result of this, as near the walls, is the gradient of the velocity in much different than the laminar case. And in general, we know that the wall shear stress, so tau wall, for turbulent boundary layer is much greater than the wall shear stress for the laminar case. And also we know that the friction coefficient CF is related to the tau wall. This is the non-dimensional form of tau wall uh, friction coefficient. Therefore, you can see why in laminar flows you can see you can have much reduced resistance of the flow compared to turbulent flow. In external aerodynamics as well, for example, when you want to minimize the drag on a wing, you need to know the boundary layer characteristics and the wall shear stress on an aircraft wing. This changes in laminar and turbulent regions, so both of them can exist on the wing. But in pipes, in internal flow, uh, no such thing happens. In pipes, once the flow is turbulent, it remains turbulent. External flows are little different, but the arguments that we have are more or less the same. So did you understand why the profile shape is different? Okay. Okay, there is a question. We said that turbulent flow from one point, excuse me. Okay, let me ask this question. We said that turbulent flow from one point of view decreases the wake of the golf ball, right? But from another point, increases the wall shear stress, so makes the friction drag higher. So how do we end up with a smaller drag on a golf ball then? At one point it decreases the wake, at one point, at the other point it increases the friction drag. Can anybody ask? Can anybody? Do you have any idea why is it happening like this? How do we end up with a smaller drag on a golf ball? No answer. There is an optimization point according to speed. Okay, your drag is kind of summation of friction drag and shape drag. You remember it, right? From the fluid mechanics. So the amount of decrease in shape drag, the decrease in shape drag, meaning that the decrease in the wake drag is higher than the increase of friction drag. So we still have a lower drag on a golf ball. Am I right? Total drag is the summation of shape drag and the friction drag. Okay. These were all conceptual arguments and questions. So from now on, we will start reviewing some of the equations and mathematics, if you are ready. And we will review fundamentals of fluid mechanics and some tensor mathematics. When we talk about scientific areas like fluid mechanics, it's different than solid mechanics. It's different in the way that we have to deal with physical processes and equations that are relevant to fields. When we talk about velocity, we talk about velocity field. So the distribution of velocity or pressure in some volume in three dimension. Now, when we talk about fields, the physical parameters that we use to characterize the fields, like the pressure field, temperature field, velocity field, momentum field, mass field, density field, everything, we have to categorize them. Uh, all of them have different mathematical properties. First, we have a scalar fields. So a scalar field is a physical variable which is a scalar. It means that at any point in space, it can be represented by only one single value. It has only one value at a certain point in space. I think there is a typo in here, so I I write temperature, for example. This temperature is a function of space and time. Okay, this double tilde in here is a kind of typo, so it is x tilde in here. If I can write somehow, let me see if I can write. So see, these double tilde things are not there like this. So uh, this x tilde, I'm it's x tilde. Okay, tilde. Tilde sign is this sign. X tilde is actually representing the space. So x, y, z to you here. X, y, and z. Or you can show y and z, x, y, and z with 1, 2, and 3 indices. So we said that a scalar, this is scalar like temperature, like pressure, like density or concentration, is a function of space and time. What we mean by field is that the variables can distributed in space. In other words, they can have different value at another point in space. So they are functions of space and also they are functions of time. So in general, they are, we write it like this, space, x tilde, and t as time. So in this class, I'm going to use this x tilde or whatever tilde. So when I put tilde sign, I'm gonna describe vector to you. Um, for example, the diffusion thing that I gave as an example in the mixing of a scalar at the scalar, over there was the concentration of paint, if you remember, concentration C. It's important to understand how scalars get mixed under different turbulent flow conditions. So uh, when I put tilde sign, under anything, I will get a vector. So the second one, the second type of field is vector field. Vector fields, unlike scalar fields, need three different values. So in here, for example, x tilde, which is a vector field of a space, needs x, y, and z, or x1, x2, and x3 values. In here, for example, velocity is a vector field. Okay, so if I write it in a vectorial notation, I put u tilde. U means velocity and tilde means vector. So this u tilde is a function of space and time. So I can show this u tilde by its three components, either u vw or u1, u2, u3. Okay? So you need three numerical values to describe the physical property of that substance, if it is a vector. Uh, and what you see in here as an index notation, we can replace this vectorial notation, tilde thing, with the index notation. So index notation, what does it say? It says that you write u and then you write I. Okay. It's a function of space and time, and I varies from 1 to 3. It means that you have ui, u1, you have u2, and you have u3. So this is called an index notation. So remember, for the vectorial notation, we put one tilde sign. For the index notation, whatever that has one index or single index, it is known as a vector. So another example, in addition to velocity, could be vorticity field. The vorticity, which is omega, in order to describe the vorticity mathematically at a certain point in a space, you need three values. So it is a vector. We know that the vorticity is in fact related to the gradient of a velocity vector. And in index notation, you are writing it like this. So what are these? These are very complex, right? No, it's not very complex. This is vorticity. It's in index notation, so you put I, so one index, because it is a vector and it is a function of space and time. So it is equal to epsilon ijk times the um, gradient of velocity. So duk dxj means the gradient of velocity. What are these I, j, k's and stuff? We'll come to that, but in the vectorial notation, it is very common that you write the vectorial notation. So vorticity, you put one tilde at the bottom of it. The vorticity vector is equal to the uh, gradient or del cross your velocity vector. Okay, so it's a cross product of two vectors. So in terms of index notation, if you, as I said, if you have a single index like I, like ui, whenever you see that, you have to understand that this is a vector. In index notation, this is a vector. Ui, this is a vector. Omega I, this is a vector. A vector always has a single index. And by the way, if I go back and see, do you see any index for these temperature, pressure, density, or concentration? No, because it doesn't have any index. It is a scalar. So one index, it is a vector. So in here, Index notation of vorticity, you see this epsilon ijk, and you see duk dxj. So what are all these ijk stuff? Uh, First of all, you see this, okay, at the left hand side. So you see a single index for omega. So directly you say that it is a vector. You see two more indices, j and k. These are not present at the left hand side, right? J and k's are at the right hand side of this equation. And by the way, are you familiar with these notations or not? Is anybody familiar with these? Should I explain these or you know them? You're familiar, but you didn't understand epsilon's notation. Okay. So as I said, in the left hand side you see only I. In the right hand side you see I, J, and K. So these J and K are not in the left hand side, right? Why I do not have J and K on the left hand side? This is what we call as dummy index or repeating index. You see that in the right hand side, how many J's you are seeing in here. One J is in here, another J is in here. So it is repeating. How many K you are seeing? One in here and one in here. So K is repeating index. Is I repeating index? No, it's not repeating index. So there is no I there. So J and K are repeating indices. If there are repeating indices in one term, they refer to actual summation. Okay, so you have to sum up those, let's say, uh, components. They do not refer to the actual physical representation of a parameter. Physical representation of the parameter vorticity is omega I. Okay, this is physical representation, omega I, which means that this is a vector. All the rest, j and k, points out to mathematical summation operation. And actually, there is a part in Pope's Turbulence book. In one appendix on tensor characteristics, you can go and you can check on that part as well. But the story is about this. These, let's say, j and k's will be summation. Like if I want to write omega 1, if I put I equal to 1 and I want to write omega 1, first of all, I have to start summing up on the j's and k's, right? But I still is the same. So I still will be 1 in all the terms that are summed up. How many terms do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I will start with j and k equal to 1, 1, and then I will fix the k to 1 and sum up on the j's. So 2, 1 and 3, 1. And then I again continue the summation with j with k equal to 2. So in these three terms, you see that the k is 2, 2, 2. It is fixed. And I summed up on j's. So j is equal to 1, 2, and 3. And then I fixed k to 3 and summed up on j equal to 1, 2, and 3. Did you understand? what is the story behind J and K. So whenever you have a dummy repeating index, J and K, you have to do the summation on these two. This is actually representing the summation, not any meaning in physical world. Is it okay? Mhm. Okay. So let's continue. So we just talked about the scalar fields and then the vector fields, and now we have the third type of the field, which is a tensor field. The example for tensor field is a stress field. Regardless of the substance, which could be fluid or solid, stress exists in both of them, and stress is the second order tensor. We generally use sigma for the stress. And for the tensor, as you can expect, we use double indices. So sigma ij is the index notation of any of the stress field. So ij is the mm, clue that you have some uh, second order tensor, not a scalar, not a vector. In vectorial notation, then, we use double tilde. So one tilde is for vector, double tilde is for the tensor notation. So this stress could be a turbulent stress, it could be a viscous stress, it could be a shear stress, normal stress, tensile stress, compression stress, exactly like in the solids. So in order to describe second order tensors like stress, uh, if you consider as a scalar with one value and a vector with three values, then a second order stress normally needs nine numerical values at a point in space. And you remember if there are certain conditions like symmetric tensor, then you would only need six values inside the tensor. So with one value to describe the tensor does not make any sense. Um, this ij index for a stress, this ij index for a stress does have a physical meaning as well. So the physical value of a stress, the physical value of a stress is some force per unit area. Okay, but this I and J shows that this force that is exerted on this area is in the jth direction, and actually it acts on a surface on this area, on this surface that has a normal in ith direction. That's why if you consider like uh, when we say um, when we have a coordinate system like x1, x2, and x3, and this cube, it could be a fluid volume, it could be a solid, it doesn't matter. When we say, for example, sigma 1, 2 in here, it means that the direction of the force is in the x2 direction because it is j equals 2, and the direction of the surface normal is in one direction. So as you can see, this square, this face of this cube is normal to the x1 axis. This is a kind of shear stress. And you see that sigma 1, 1, sigma 2, 2, and sigma 3, 3 are what we call as normal stresses because those stresses are generated by forces that are acting parallel to the normal of those surfaces. So, uh, um, because this force is acting along the surface normal vector, we call it normal stress. Okay, stress is the most well-known tensor, but in fluid mechanics we have other tensors which are very critical in terms of understanding turbulence, generation of turbulence and modeling turbulence. One of the most well-known tensors is what we call as velocity gradient tensor. Okay, velocity gradient. I have again uh, two indices in here, I and j, so it's a second order tensor as well. And similar to the stress, this also requires nine different values at a certain point in space to be described. And in terms of vectorial notation, you see that this has two tilde signs, and this is del of your velocity vector. When we write Navier-Stokes equations, to be able to solve or model the turbulence, you have all those things that we just talked about. You have scalars like this pressure in here. You have the vectors. Yeah, you see the vector I, ui, uj is a vector, ui is a vector, and like and you do have tensors because you have gradients of velocity. Okay, because there is a velocity gradient, there is a velocity gradient, there is a tensor there as well. See, this is the velocity gradient. When we apply Reynolds averaging to Navier-Stokes equations, so we come up with this Rans equation, uh, we end up with stresses as well. So Navier-Stokes equations incorporate all of these scalars, vectors, and especially second-order tensors all at the same time. So we do need to understand the properties of these second-order tensors. And I'm assuming that you got exposed to tensors sometime in your life. So what I expect from you is to read that appendix from Pope's book. We do not we do need actually to know mathematical properties of tensors so we can apply them in turbulence. Before we start talking about the properties of second order tensors, there are some special tensors that we only need to use them just for mathematical representation. And they generally do not have a physical meaning, but they have to appear in equations. And when you see them, you shouldn't be surprised. We just need to know how to handle these. So delta ij is the unit tensor or Kronecker delta. Its definition is like this: delta ij, so when you see I and j, it suggests you that this is a tensor. And the definition is that when I is equal to j, it is 1. When I is not equal to j, it is 0. And I and j is from 1 to 3. So in tensor, in vectorial form, it is a 3 by 3 matrix. So delta 1, 1, delta 2, 2, and delta 3, 3 are 1, and the rest will be 0. So these are the properties of uh, the property of delta ij. First of all, is that the trace of delta ij is equal to delta ii. Trace, you know what is the trace. The trace of a matrix is the summation of the main diagonal, right? So the trace of this matrix is 1 plus 1 plus 1, which equals to 3. So when I write delta I mean uh, I have a repeating index, II. It means that I have to do summation on this. Summation from what to what? From 1 to 3. So delta II means delta 1, 1 plus delta 2, 2 plus delta 3, 3. Delta 1, 1 is 1. This is 1. This is 1. So 1 plus 1 plus 1 is equal to 3. So this is a property of unit tensor or Kronecker delta tensor. Do you understand these? These are the basic mathematics. So, but you have to know all of these tensorial notations and initial notations as well. Is there any problem? Okay. The second one is actually the uh, let me just. Mhm. The second one is the alternating symbol. So what is it? The alternating symbol. We remember it as Levi-Civita symbol. Levi-Civita symbol. It is epsilon ijk. So you've seen this in the definition of vorticity. Remember, the definition of epsilon ijk is like this. It is equal to 1, minus 1, and 0. And whenever you have a cyclic distribution, it is equal to 1. Whenever it has anti-cyclic distribution, it is minus 1, and otherwise it is 0. What is cyclic distribution and anti-cyclic distribution? You see it in here. So cyclic means that it is counterclockwise. So 1 to 2, 2 to 3, and 3 to 1. It means cyclic distribution. Anticyclic means that you just have your 1, 2, and 3, but it is clockwise. So see, for example, if it is 1, 2, 3, or it is 2, 3, 1, or it is 3, 1, 2, it will give you 1. Anticyclic is like this. If it is 1, 3, 2, 3, 2, 1, or 2, 1, 3, it gives you minus 1. And if it is, for example, epsilon of 2, 2, 3, then it will be 0. Or 1, 1, 2, it will be 0. So this is alternating symbol. So this alternating symbol, if you have, for example, a cross product, vector cross product, you can use this alternating symbol. How? Actually, you can see that if you want to cross product two uh, vectors like u vector and v vector, you can write it like this. So your r vector, which is a cross product of u and v, will be epsilon ijk ei ui uj vk. And in vectorial notation, you can write it like this. You remember this vectorial or matrix notation from maybe in your uh, high school, even in your high school. So you have the normal vectors E1, E2, and E3, and then you have U1, U2, U3, V1, V2, V3. And also you remember that we use this alternating symbol in the definition of the vorticity vector as well. So before giving the properties of second order tensors, we give some examples of tensors, and we just said that the gradient, velocity gradient, is a second order tensor. The viscous stress tensor that you have both in fluid mechanics, and also you have this tensor in solids, sigma ij. And also, when I was uh, discussing about the Reynolds average Navier-Stokes, I said that we have another additional term in Rance equations that we know them as turbulent or Reynolds stress tensor, and these are the tensors like this. So two fluctuating velocities are multiplied together and then gets averaged. These are kind of Reynolds stress tensor. So one of the properties of let's consider that you have a general second order tensor that is tensor B, and in the index notation you show it by a small b ij, right? Because you have ij, it is a tensor, second order tensor, and in vectorial notation it is a 3 by 3 matrix. So let's suppose that this is a general second order tensor. The first property of this tensor is the contraction. So contraction means that um, means the trace of B. By the way, how much time do we have? Is it? I think we have until 5 o'clock, but okay, let's finish this page and then we can stop here and then we can continue next week. The contraction means trace. So trace, as I said, is the summation of the diagonal elements. So contraction, BII, it's a dummy or repeating index. It means summation. Summation means B11 plus B22 plus B33, right? So this is actually your contraction or the trace of tensor B. So why is it important to us? Because the value of trace, the value of contraction, can be used to decompose second order tensors. Normally, when we want to decompose tensors, second order tensors, like this Bij, we can decompose it into two parts. One part is called isotropic part, and one is called deviatoric part. So isotropic, as the name suggests, it says that it is not changing with respect to direction. So it means that when you have a tensor, if you just get the isotropic part of that tensor, this isotropic part, if you change the uh, how can I say, the direction, if you rotate your frame of reference, for example, XYZ, the values inside that second order tensor, the isotropic part of the second order tensor, will not change. Okay? The deviatoric part, as the name suggests, is the part that when you rotate your frame of reference, it will change. And also you can decompose this deviatory part into symmetric and anti-symmetric part. We will see all the details later about this.